Good morning, everyone. My name is Ayushman Datta, and today I'm presenting our work Margin Adaptation, Enhanced Label Distribution Aware Margins with Strategic Reweighting and Representation Optimization. This work has been done in collaboration with Priyobrata Mondal and Professor Swagatam Das. Modern machine learning systems, especially deep neural networks, face a persistent challenge, which is class imbalance. When some classes have many samples and others have very few, the model becomes biased towards the majority. This is especially critical in domains such as medical diagnosis, fraud detection, and autonomous systems. Traditional training methods fail in these scenarios because the learning process is dominated by the majority class. So we need not only a better loss function, but also better calibration of representation and training dynamics. To formalize the problem, we consider a dataset with C classes, each containing a different number of samples. The imbalance ratio rho, which is the smallest, which is the ratio of the smallest to the largest class, tells us how skewed the dataset is. When this ratio is very close to zero, it tells us the model that the dataset is very severely imbalanced. And when the ratio is very small, the model struggles to learn meaningful features for minority classes. Thus, our objective is to adjust margins, weights, and representation learning to account for class distribution. Cross entropy is a standard loss for classification, but it treats every class equally. This means minority classes receive very weak gradient signals. As a result, decision boundaries favor the majority. Minority samples do not influence training strongly, and the model develops a biased feature space. Cross entropy is fundamentally unaware of class imbalance. LDAM improves upon this by introducing label distribution aware margins, giving minority classes higher margins. This pushes the decision boundary towards the majority class, giving minority samples more space. However, LDAM still faces issues. The margins are not dynamic, it does not interact with representation learning, and it does not adapt across training epochs. These limitations motivated us to design an enhanced formulation. Our enhanced LDAM introduces three key innovations: temperature scaling, adaptive margins based on class frequency, and strategic reweighting across training. The temperature scaling allows us to control the softness of the logits, improving the gradient flow and stabilizing training. Instead of static margins, the margins dynamically depend on how underrepresented a class is. We vary the reweighting parameter beta over time, giving the model stability in the early stages and stronger minority emphasis later. We extend the enhanced LDAM by integrating dynamic class weights. These weights adjust continuously based on class frequency and training progress. This ensures that minority class samples consistently receive the importance they require, but without over penalizing majority classes. Our complete loss function is a summation of loss of weighted and contrastive loss. Contrastive learning ensures minority classes uh, become compact and different classes remain well separated. This directly strengthens representation quality. Our training pipeline follows these steps. First, we compute the class frequencies, then we initialize frequency aware margins. For each epoch, we compute an evolving beta parameter. In our fourth step, we normalize the features. And in the second to last step, we compute enhanced LDAM and contrastive loss and get the final loss. We then update the parameters with a scheduled learning rate. This multi-stage optimization ensures stable, robust learning even under severe imbalance. In our results, we can see we have done a study across multiple data sets like MNIST, FMNIST, and we have taken imbalance cipher 10 at imbalance ratio of 0.1 to 0.01, cipher 100 of 0.1 to 0.01, organ CMNIST, organ SMNIST, and organ and tissue MNIST. We can see that our model has outperformed the state of the art models that are present in the market by a considerable margin. In our ablation study, we have evaluated the variations that are resulted from the different learning rates. We have gotten the results from variations in weight decay. We have gotten the results from variations in temperature, and we have done a runtime comparison between different data sets and between our model and other models that are comparable to us. And you can see that LDAM has consistently outperformed like LDAM BRW and other models in the runtime space as well. In conclusion, we proposed a margin adaptation framework guided by distribution calibration. Our enhanced LDAM incorporates adaptive margins, temperature scaling, and dynamic reweighting. We have integrated supervised contrastive learning for feature level robustness. Our results show that with physics inspired modeling and margin aware optimization, even severely underrepresented classes can be effectively learned. Thank you.